Okay. Work equals change in kinetic energy. Work equals force times distance. It doesn't really matter which one you choose to use here. Both will give you what you're looking for. The information that they give you is that we've got a mass of 2 kilograms. That's a huge puck. We've got an acceleration of 5 meters per second squared. We know that the distance of the acceleration is half a meter. Okay, so you could use this information in changing kinetic energy. You just have to, we would assume that the initial velocity was 0 and that it now has, we have to find VF using this information, using VF equals, VF squared equals VI squared plus 2AD. We could find VF because we know A, we know D, and we're assuming VI to be 0. Because it doesn't actually matter what initial kinetic energy is or what the initial velocity is. All we care about is the change in kinetic energy. So if we assume it's 0 and then we find VF, or it'd be the same if it were 5 and we found VF, or 10 and then found VF. So you can use this to find change in kinetic energy, or you can use these two things right here, the mass and the acceleration, to find the force required to do that, because force is equal to a mass times an acceleration times by the distance. Either one should get you the same value. Is that enough, or do you want me to see more? Okay. Anybody else? Hands up. Connor, you want to see number 5? A 3-meter long ramp. No, girl uses a 3-meter long ramp to push her 110-kilogram motorbike up to a trailer, the floor of which is 1.2 meters above the ground. How much work was done on the motorbike? So there's a couple ways to do this one as well.
And that's screwed up with the ramp thing.
So we've got a motorbike on the ramp. We know the ramp is how long?
3 meters.
This distance here is 3 meters. Do we know the angle of the ramp? We do not know the ramp. We know that this is 1.2 meters.
Yeah.
Okay, so, yes, Jasmine. It's very helpful. Because we're using, some will require it, some will not. I will recommend you, I recommend you will absolutely do them. Unless I specifically ask for a free body diagram, technically you don't, but you should, this should be a habit you get into, is drawing the picture. The only reason I sometimes do and sometimes don't is because just by reading the question, I know where it's going to be useful because I know where it's going, because that's literally my job. But you guys don't necessarily, some of you may, and that's great, and some of you may not. By asking the question, I'm willing to bet we don't totally know where this question's going. And so it's important to put everything down, especially for you guys, to figure out, you know, where we're going to go from here. So there's 2 ways you can approach this particular question. Again, and it's the same 2 ways that we looked at previously. Either we're going to use work is equal to the change in energy, or work is going to be equal to a force times a distance. In the previous one, I knew it was going to be a change in kinetic energy because we're accelerating an object. If she's pushing, we're going to make a few assumptions here. If she's pushing a motorbike up a ramp, the easiest way to do that is to make sure that the motorbike is traveling at what velocity? A constant velocity. Doesn't matter what it is as long as it's constant and non-zero.
It says it's constant.
Does it actually say it's constant? It does not say it's constant. So, because this is constant, we're not changing kinetic energy, so the change in energy isn't going to be kinetic. What energy are we changing, though?
Potential?
Yeah, because we're lifting, effectively what we're doing is we're lifting the bike up. We're just doing it over a distance. Now, if you wanted to use work equals change in energy, so this is going to be a change in potential energy, specifically gravitational potential energy. This is going to be mgh in, final minus mgh initial. Where do we want to call 0 if we're going to call...
Ground.
Yeah, if this here is what we're going to call the height equal to 0, makes sense, then this term is gone, and the work is just going to equal the mass of the bike, which was 110 kilos, times 9.8, times the height the object was raised. That'll give you the work, whatever that value is.
That's the answer?
Yes.
Wow, I got it.
Why are you asking the question then? Like you did it in your homework?
I wasn't sure, because I thought...
But there's an
I
answer
had
key at the
some
bottom.
bigger one. Yeah, I know, but I didn't find it too helpful.
What was your number? What was your answer?
City? Well,
No, what's your what's the number?
1293.6.
1293 1293.6. The answer is 1.3 times 10 to the 3 joules. Yeah, so the answer is right there. Literally right there.
Yeah, I know, but I was...
But yes, you did it right. You did it right. But you know what? Now I'm going to make you sit through the other way you could have done this problem.
Okay.
If we assume that the bike is moving at constant velocity, because that's the easiest way to do this, then the acceleration is 0, yes. So the forces then must be balanced. What forces are going to be balanced?
Your acceleration, or sorry, not acceleration, your F applied, and
The F applied upwards, you betcha.
gravity and normal force.
Normal force is going to be that way. Gravity straight down. Those are not equal and opposite.
No,
So no, those are not balanced. Because we're on an incline. Which
yeah, so...
you did we did inclines last chapter.
I know.
So what is balanced with Fn and Fa? Fg parallel and Fg perpendicular. Here's my Fg perpendicular to the incline. That's going to balance out with my Fn. This right here is my Fg parallel. That's going to balance out with my Fa. This angle is not given to us, but we can find it. How are we going to find it? SOHCAHTOA using what information, Manuel? That guy and that guy. You betcha. Opposite and hypotenuse. You betcha. So theta is going to equal the sine inverse of the opposite side, 1.2 over 3. So we can use this angle, because that angle is going to be the same as that angle, which I've proven to you already, to give us Fg parallel, which is going to give us Fa, which we can then just plug in here, and we know that the ramp's 3 meters long, and that's going to give you the exact same value. So we could have done it that way as well. So, but Connor, yes, if you want to use a change in potential energy, you're absolutely correct to do so. Comments, questions, concerns? Cool. Anything else? Yes, you're here. What was your answer?
Yeah, I agree with that.
Then this is a good one to do. Which question you said this was? 6? No, 5. No. 7. A force of 50 newtons is used to do 480 joules of work to move an object. What distance? Oh, that's just a straight division question. Yes, so I see why this is problematic.
Yeah.
480 divided by 50. I'm going to assume that we all punched that into our calculator properly.
There's no like M or
9.6. And there's nothing given to you in meters. This is a good question to ask about. Yeah, if you got 9.6, that would be a correct value. I don't know why it's not there. This particular answer key is lacking. No, but that 9.6 is correct. Anything else? Okay. There were the spring questions I assigned. Did anyone take a look at those?
Actually, I'm kind of a little bit...
Number 5 on the spring question for Canwar. Okay, here we go. Okay. A man with a weight of 9... Oh, yeah, and I didn't give you an answer key for this one. A man with a weight of 900 newtons. So we know Fg is 900. Lies down on a spring-loaded mattress. The combined force constant of all the springs in the mattress is 18,000 newtons per meter. So it's treating all the springs as one massive spring. How much elastic potential energy is stored in the bed's springs?
Is this not like a change question?
Sorry?
Like a change like a change in initial versus a change in final?
No, this is not a work question.
Okay.
This one just wants potential energy. It says, how much elastic potential energy is stored in the bed springs? So potential energy is... Ooh, hey, this could be a really tricky question to do.
Yes.
Because it's half kx squared. Interesting. We don't know what x is going to be, but we know k is 18,000. So we're going to 1/2 times 18,000 and then something squared. Okay, so here's a question for you. How are we going to go about finding the other, well, in this case it's going to be a compression, but how are we going to find the extension of the spring? So we've got a spring. Let's just assume it's one big spring, and we're compressing it by some amount. And this is what we're going to call x. We don't know what that is. But there are two forces here. One is going to be the F spring is pushing back on this. What's causing it to be compressed?
Oh, wait. Or, sorry,
No, you're right. Yeah, you're right. Oh, wait.
mass.
Well, but we're given the weight. You were right the first time.
You were right, dude.
So a weight of 900 newtons is compressing this gigantic spring. Well, how far? We know Fs is equal to Kx. And we know that, I mean, you're lying on a bed. The bed's not going to spontaneously fling you up into the sky, and you're not like crushing the bed down into the ground. You find a happy medium. So we know these two have to be equal. So Kx is going to equal 900, and we know that the K value is 18,000 newtons per meter. So we can use that to find x. 900 over 18,000. So that's going to cancel, that's going to cancel. This is going to be 9 over 180. That's going to be 1/20th, which is 0.00? No. 0.05 or 0.005? 0.05. Is what I got. Did you use calculator? You did not. Okay. 0.05 meters. So then this value for the distance is going to get plugged in there. And we're going to find that the potential energy is going to equal 1/2 times 18,000 times 0.05 squared, which is going to be 18,000 times 0.05 squared. I got 22.5 joules. Of potential energy. So not a lot. That was your answer? Yeah, good job.
Can we do number 1?
The keys on a computer key contain small springs that compress by 4.8 millimeters when a key is pressed. On a particular day, 12,500 keystrokes are made on the keyboard. The springs in the keys have a constant of 2.5 newtons per meter. How much energy was supplied to make all the keystrokes performed that day? Did you do number 1?
I did.
What was your value? What was your answer?
It was 0.36 joules. I just questioned that.
Well, we know Canwar got number 5 right. Did anyone else get a value for number 1? Canwar, what'd you get? It's the same thing.
You did? Good.
So, physics by democracy with anybody else? Did anyone get a different value? Did anyone else attempt? Did only these 2 guys attempt this question? But we don't know where to go. Okay, do you want to see it then? Okay, so let's try it. The 2 of you, though, should feel pretty good about the fact that you got the same value. So here we go. Keystrokes on a computer, fire, small springs. Okay, so the compression, we are told, is 4.8 millimeters, which is going to be 0.0048 meters. Because that's going to be centimeters right there, so that's, yeah. We are told the spring constant is 2.5 newtons per meter. And we are told that there are 12,500 keystrokes. How much energy was supplied to make all the keystrokes performed that day? So, the energy we want PE equals 1/2 kx squared. So the energy for one keystroke is going to be 1/2 times k value of 2.5 times 0.0048 squared. That'll be the potential energy of one keystroke. And then you take that value and you multiply it by 12,500 to give you all of the keystrokes. Canwar, Connor, is this what we did? Yeah. So then your value of 0.36 joules has to be correct. It's the fact that this value is really, really small. Really, yep, impacts how much energy is there. Cool. Anybody else? What did we get for the other ones? Question number 2?
I got number 2 is 3.5 meters.
Canwar? Number 3?
16.
Newtons per meter. Canwar? You got?
Yeah, I got the same.
Oh, okay.
For that, I got 90.
Oh, for number 4.
Yeah, 90.
For number 4, you got 90. Oh, I was verifying if you got the same value as 3. So for number 4, you got 90.
I got 92.
90 joules.
Yeah.
Okay, so there you go. I feel like Canwar and Connor have proven themselves enough with some of these other ones that we can take these values as truth. If anyone wants me to go, if you get a value that's not in line with what these gentlemen got, let me know, and we can look at it further. But we're gonna assume that those are correct. Okay. Comments, questions, concerns? We're good.
Let's do horsepower.
Moving on. Okay, I would like to do horsepower today. There's 2 things we have to do today. We're gonna look at another way to find. So yeah, grab your notes if you haven't already. We're going to look at another way to find work. We've got 2 formulations for work. This is going to be the 3rd formulation for work. Just so we're clear here, we are now in this section of the formula sheet right here. And I want you to see what's present and what is not. We've got, oh, and do grab a pen. We're going to add something to this list.
Like a pen or a pencil?
A pen. A more permanent writing utensil. So we've got energy potential, and this is going to be EPG. Gravitational potential energy is MGH. Kinetic energy is 1/2 mv squared, which I've already given to you there. And then the last one, we're going to add it on the left-hand side here. The other one that we've used here We'll just call it EP spring. I'll just in the same format as everything else here. We have 1/2 kx squared. This was our first formulation for work. Work is equal to a force times a distance. The second formulation I gave you was that work was equal to a change in energy, which I wrote down first as work equals delta E, which is final energy minus initial energy. The way the formula sheet gives it to you is actually using this expression here. If you see if I solve this for W, it's going to give me, like I'm going to subtract EI over here, so it's going to be energy final minus energy initial, so this is work equals change in energy. But this, the way this is quoted for you here, we're going to actually introduce to you as the law of conservation of energy, either tomorrow or the next day. So this is going to be the way that it's written for us. So the only one we need to add is this one here. Everything else is there. So let's continue. Manuel, we good? Okay. Connor, don't scare your classmates. Another way to find work. This way is not going to be given to you on your formula sheet. This is a technique you need to remember. Another way to find work is to use what's called a force displacement diagram. In the notes on this page. Okay? This is most useful when? No. Yes, but no. When do we need? Because we could always use a force displacement graph, right? Like, if I told you the force was, what was the value from the homework? If I tell you that the force is 5,000 newtons and the displacement was 40 meters, what would this graph look like? What would a force displacement graph look like for a 5,000 newton force over 40 meters? Who said that? Louder. It'd be a flat, straight line, right? Like it would look like, so if I go over here, it would look like this. So there's my straight line at 5,000. Here it is at 40 newtons, or 40 meters. All we did was multiply these together, right? In the question. Force times the distance. But if I graph it, well, what have I found? Well, I've actually found the area here. Because a rectangle is a length times width. So I've just done force times distance is the area underneath this graph. How is this question different than this question? You don't have an acceleration. We don't necessarily have an acceleration. We have an increasing force. That is the important piece here. I'm not going to say increase, I'm going to say change.
In a constant way, the line's not curved or anything else?
We could still do it if we curved it. You would just need calculus for that. So I don't want to write down that, I don't want to exclude that possibility for you later. So I'm going to just quote it like this. For the math, you know, yes, we require a constant change. What are some example, or what is an example of a situation where the force is going to change as you apply it?
When we had that spring polar Newton gauge thing.
Yep.
When we pull that back, that's increasing the newtons.
What were you actually doing with that thing? Can you grab the door, Tristan?
Something solid and pulling.
No, even more fundamental than that.
Spring.
Yes.
The spring.
Well, what was happening inside that thing as you were pulling on it?
There's a spring that was being pulled apart.
Yes. So a really easy example of this, of an application of this, is when springs are involved. Because you are required to increase the force to change the extension on a spring. So if I give you a graph like this and I say, okay, well, what is the work being done here I've already kind of outlined it for us here. Work is the area under a force distance graph. So if I give you a graph like this and I say, okay, I want to find the work done required to move this object from 2 meters to 6 meters, given this information, all we've got to do now is break this graph up into this section and figure out the areas. So let's do it. So I want from here to there.
Well, to screw it up and make it easier for yourself, I would break it up into 2 boxes.
I was just going to ask if there was a way I could make it easier for myself.
So the bottom box, so you cut it off with a 1 line. and then-
Oh, that's a horrible idea. You're on the right track, but that was a horrible. Where you want me to cut the box is a horrible idea.
Yeah, I know. I mean like a little bit higher.
Like a little bit higher. So like at what value? At what value, Connor, might this be?
I would say a little bit under 1.5. It looks like.
Yeah, keep going.
Maybe 1 3/4.
That's above 1.5. You said a little bit below 1.5.
I give up.
No, Connor, no, you're not allowed to give up because you're actually correct. You want it a little bit below 1.5. 1.5 is 1.5.
Yes.
So what? So I'm going to draw what he's trying to do. He wants me to cut the thing right here, which is absolutely where you should want to cut this thing, because that's where 2 connects with the line for our increasing force. But what we got to figure out here is what is that value? What is a reasonable estimate for that value? It's definitely not 1.8. Because this right here, Manuel, we've already established is 1.5. Thanks for coming out. 1.4 would be a great one. Because 1.3 is just barely over halfway, right? Between 1 and 1.5, halfway is 1.25. So we know we're over halfway. Calling this 1.4 is actually the most reasonable guess. Well done, Tristan. So if that's 1.4, what else are we going to have to estimate here? Because we're going up to 6. 6 ends right there. What might this value be? If you called that thing 2.7, you'd be reasonable. If you called that thing 2.75, also reasonable. So now I want to find this area here. And I want to find this area here. And then I'm going to add them together. So the area of our triangle is what? Formula is? Yeah, 1/2 the base times the height. The length of the base is? Good. And what's my height? Yeah, 1.4 to 2.7. Good. 1.3. Love it. He's correct. Thank you, Zaid. And then the last one in pink, that's the easier of the two, right?
What?
That's just a rectangle. Rectangle's the length times the width. That's just going to be my length is 4. My width is 1.4. 4 times 1.4 is? Anybody? You betcha. So then the total work done 8.2 joules. Love it. Questions, comments, concerns about the technique here? This is, in fact, this is how we have to do it if we've got an increasing force. Okay, I want you guys to do the next one. Find the work done in the moving object from 4 to 10 meters. Go. If you got a value, let me know. You betcha. Cool. So, as you heard from two opposite corners of the classroom, the value you're looking for is 18 joules. I'll give you a couple more seconds, those of you who haven't quite finished it yet. That's the value you're looking for. Comments, questions, concerns? Anyone not able to find that value?
Would that be able to be done with our physics level to figure out what is listening? Yeah, but it makes sense. But it's done with listening to well, you want to start where it's the lowest value of 104. That's the question. Where the first the lower distance is that map. The line is that where you do education with you, right? I mean, you could cut it where you did, but then you have a triangle there, a triangle here, a rectangle here, a rectangle here. How that? One of those
So there's one more
I was supposed to try.
one more concept that we're gonna. We might not get to the horsepower today. We might have to save that tomorrow for the double block, or for the not double block, the short block. No, tomorrow's double block's my math class. So you guys are tomorrow's bad seed. Leave you last.
Okay, you scared me.
Okay, so the last concept though that I want to introduce you to in this first section here. So we've done work. We've done 3 different kinds of energy. Angelina, did you get it? Okay. We did work, we did 3 different kinds of energy, and those are the only kinds of energy that we're going to look at over the course of this chapter. Now we're going to take a look at, and then we looked at a different way of finding work. Now I want to connect all of this to the idea here of power. Now, what power is how quickly you can do the work, or work per unit time. So what that's going to end up looking like here is power is going to be given to us as work over time. I'll actually write out the word down there. But if we look at what's happening here, this is where we're going to connect to horsepower. What was our first formulation for work?
W equals FD.
FD, right. So power then I can just rewrite as FD over T. But what's D over T?
D, velocity.
Specifically, what kind of velocity? You're never going to live that one down. But yes, what kind of velocity specifically? Average or constant? Yes. Either it's not changing or they give you the average velocity. Absolutely. This value right here is either average velocity, if they give you the average velocity, or you can assume that's a constant velocity. Constant. And so what that gives us is this other formulation for power, where power is equal to a force times how fast the object is moving. Now, these 2 formulations are both given to you on your formula sheet as well. Here it is, P equals W over T, and P equals F times V. There they both are. Now, does anyone know the scientific unit for power? It's watts. Who said that? Yes, correct. It is watts. Also, so watts is, and here's, now we're going to get even more confusing here. Watts is big W, which also looked like work. So you just need to remember where big W is being used as a unit and where big W is being used in a formula. Now, they do double duty, and so now you have to start being careful with things like that. Sorry? It's the same, yeah. It's just, yeah, it's the same. So that one is because current is defined as,
What about light?
we'll get there. Power is watts per time. The current is charge per second past a particular point in a wire. And there's a relationship between the force on that charge. Yeah, so it's a similar form. We'll get there. Actually, our last unit will be our last unit, or will it be the next unit? We are going to do circuits, and we'll address it when we hit circuits. Power is measured in watts, big W. Power is also measured in another set of units. Work was measured in what? Time is measured in? So a watt is actually just a joule per second. But rather than talking about joules per second, we had another old guy who wanted to be included. So we gave it the unit watts, which is named after a guy last name Watt. Also, power is referred to as horsepower, and to give it a value, 1 horsepower is 746 watts. Now, where that value came from, I have no idea.
Is it active? Maybe
It's defined to be that way.
maybe it doesn't work, right?
1 horsepower is 740. Right now, no, I can't, because by filming these lessons, it slows my computer way the heck down. So I don't want to do it right now, but I will later. 1 horsepower is defined to be 746 watts. Like, I don't know what horse they used, because a Clydesdale is going to be different than like a miniature. But here we go. So some examples of what a question could look like here would be if a 30-kilogram object is lifted 20 meters straight up in 2 minutes, what was the power used to do that? So if we've got a 30-kilogram object lifted 20 meters in 2 minutes. So, what's going on? Okay, so what you're doing here, because this thing's being lifted straight up, let's draw it. What you're suggesting here is that this is a change in potential energy. So I've got a 30-kilogram object, and I'm raising it up. Somehow it got a little bit bigger. Now, it was lifted 20 meters. So what you're talking about here, Connor, is that this is a change in potential energy. Cool. So we're going to use that work is equal to change in potential energy to figure out how much work was done. So what I'm hearing you, the way I'm seeing you want to take this, is that power is equal to work divided by time. So my potential energy, that's just going to be my mg height final minus mg height initial equals work. Well, where do we want to call 0? Makes sense to call ground level 0. What is then work going to be equal to? Mass is 30, g is 9.8, the height is 20. 5,880 joules of work done. Love it. How long did it take?
120 seconds.
120 seconds. Time is always measured in seconds, unless you're told otherwise. So how much power was required to lift that object?
Fine, 49.
49 what?
Horsepower.
No.
Sorry, watts.
Thank you. Could we have done this question any other way? How else could we have done this question? Connor went and he found the work that was done to raise the object by using a change in potential energy, and then we divided it by the 120 seconds. How else could we have done this question?
Oh man, it's only like 0.06 horsepower.
Well, we also know, or maybe we don't because you guys are being really quiet, P equals F times V. Could we have figured out how fast that block was moving up? How fast is that block moving up?
Like 120 seconds. Or sorry, you're looking for acceleration.
No, I'm not. I want to know how fast that block was being raised. How would you tell me how we do it?
Yeah, exactly.
V equals what, sorry? D over T. Our d is 20. The t is 120 seconds. What's the velocity?
1.6 repeated. Sorry, 0.16 repeated.
Like 0.161616 or 0.16666666? Okay. Okay. And that's a constant velocity. So what forces are acting on my object here? There's gravity straight downwards. What else is acting on our block? There has to be an applied force upwards lifting this thing, right? And because this is a constant velocity, what do you know about these two?
They're balanced.
They're balanced. So my applied force is going to equal Fg. So
Technically a normal force in
that's
between.
going to be m times g times v. So it's going to be 30 times 9.8 times 0.16 repeating. What's that value? It had better be 49. Did you actually calculate it? Sweet. So it doesn't matter how you approach a question like this. There's a whole bunch of different ways to come about to the final, ultimately, hopefully, correct answer. Two more examples. How long does it take what does that little K there mean? That's a kilowatt. Cool. A 2 kilowatt kettle to do 50,000 joules of work. 2 kilowatts is how many watts? Cool. And if so, I want to know how long it takes a 2 kilowatt kettle to do 50,000 joules of work. What's the formula I'm going to use here? What have we been given here?
Kilowatt.
Which is a measurement of, sorry, Manuel? We've given power. This is power. And we want to find the amount of work done. No, we want to find how long it takes, the time, to do this much work, the 50,000 joules of work. So power is going to equal work over time. We know that this is a 2,000 watt kettle. We want to figure out how long it's going to take to do 50,000 joules worth of work. How long is it going to take?
$25.
25 seconds. Cool. Love it. Thanks, Tenjo. Very quick kettle. Okay, last one. Yes, Khalil. Lunch is in 15 minutes. Can you hold it? Or is it? If I'll let you decide. I'm going to do one more example. An 80 kilogram person can run up a flight of stairs in 2.1 seconds. If they gain 1.7 meters in height, what is the power of the person? So, what's happening here?
Yo, guys running upstairs.
Guys are running upstairs. This is what you're going to do for me tomorrow.
He's pretty quick.
He's really short, too. He's climbing upstairs. It's my daughter. Actually, at a time, this would have actually been a pretty good representation of my daughter, almost to scale. But there's no chance she's going to do this in 2.1 seconds. What was the power? Well, we want power. What's the formulation we're going to use here? Could we use FE? We could use FV. What's the force being applied by the person? It's going to have to be equal to gravity. So we're assuming the person is not accelerating up the stairs. We're assuming they're going a constant velocity up the stairs. Okay? So if we're going to use P equals FV, the force that we're going to use is equal to gravity times the velocity. Velocity is going to be given to us by d divided by t. So we can figure out force of gravity is just going to be mg times d over t. We can plug this in. We have an 80 kilogram person times the acceleration due to gravity times the vertical distance, 1.7 meters, divided by 2.1 seconds. What is the power produced by that person? $634 point, what was the point, what? Okay, so let's, 6 repeating watts. Cool. How much horsepower is that? Hey, what's up? Okay, thanks. Bye. Ravneet. You know you're going to the dentist today, right? Surprise! You're going to the dentist right now. Your mom's here. Bye. How much horsepower is that?
No, 0.85.
Cool. Love it. Yes, you do. And I'd like you to start it with the time that we have remaining. I am going to give you a chunk of homework to do. Ravneet, just real easy. There's 8 more questions there. And there's 1, 2, 3, 4, 5 more questions there. Basically, it's everything else. Okay? This is Monday's homework. And Monday's homework. There you go. Give it a shot. Tomorrow, I know I said I wanted to do it today, but we took too much time at the beginning of class, and that's fine. Tomorrow, we are going to do this. We're going to start class with the Stairmaster Lab. You guys are going to figure out what your horsepower is. It's going to be great. Please do use this time. Start this stuff. When the bell goes, you may pack up.